These are probability notes for permutations. Today we're going to calculate permutations where all elements are arranged, and we're also going to calculate permutations where some elements are arranged. A permutation is arrangement of a sequence. This is a sequence of Duplo blocks. They come in green, red, and blue. This is an arrangement or a permutation. If I move the red block to the very top, this is a different arrangement or a different permutation. If I move the red block to the bottom, here's another permutation. A permutation is just another word for an arrangement. And in this class, we often do permutations involving values or letters or numbers. These arrangements involve no replacement, so we're not doing any replacement. Once we use a value, it's done. For example, if you take the letters in the word sum, MSU would be a permutation or arrangement of those three letters. However, mum is not a permutation of the word sum because once the M is chosen the first time, we cannot come back and use it a second time. It's just those three letters arranged in a different order. Let's take a look at a few examples. In problem 1, Al, Bo, Ed, Flo, and Joe are competing for first through fifth places in a race. How many different finishes of these 5 athletes are possible? Well, we know that there are 5 different places these athletes could finish in. One of these players is the winner. And there's 5 to choose from. So one of these 5 people win. Those are the different people that could finish first. Let's say it was Al. If Al finishes first, there's 4 different people that could finish in second place. Let's say Bo does. That leaves 3 different people for third place. Let's say it's Ed. Now there's only 2 people left to compete for fourth place. Let's say Flo wins. And we're left with just Joe in fifth place. So once we know the first 4 finishers, there's only 1 person to choose from for fifth place. To find the number of different finishes possible, we do 5 times 4 times 3 times 2 times 1. That's equal to 5 factorial or 120. Based on this information, see if you can solve 2, 3a, and 3b. If we have 4 pictures on a wall, the number of arrangements, well, we have 4 choices for the first picture. Once we choose that picture, there are 3 pictures left for the next position. Once we pick another picture, there's only 2 pictures left to choose from. That will go in the third position. And then for the last picture, well, we've already used the other 3 pictures. There's 1 left. This is equal to 4 factorial or 24. For permutations of the letters of the word sum, there are 3 letters to choose from for the first letter. So you can pick one of those letters. Let's say it was S. You have 2 letters to choose from for the second position. Let's say you choose M this time. And then that leaves us with 1 letter for the last position. 3 times 2 times 1 is 3 factorial or 6. To list these permutations, we have sum and MSU. There's a few others. We know there's 6 altogether. So if we look at the different arrangements, you probably have things like SMU, MUS, USM, and yeah, that's it. If all the elements are being arranged in your set, then there are n factorial permutations of n different objects. We're now going to look at calculating permutations where some elements are arranged. In example 4, we have our same 5 athletes competing for a medal in a race. The winner gets a gold medal, second place gets silver, third place gets bronze. How many different ways can the 3 medals be determined? Well, for one of the options, you could figure out the number of athletes that could win gold. There's 5 choices. Let's say Al wins gold. For silver, there are 4 athletes left, assuming Al can't win again. That gives us 4 choices for silver. Let's say Bo wins silver. For bronze, we have 3 athletes to choose from. Assuming that Al and Bo can't win, there are 3 athletes left. And we don't have any 4th or 5th place participation trophies. So in this problem, we just do 5 times 4 times 3. That's equal to 60. And the idea is you start with the first number, you subtract 1 from that, you subtract 2 from that, and if you had more places, you could continue to subtract 1 to get more options. In this case, we do 5 times 4 times 3. On the next side here, if you look at option 2, we have this formula that says kind of a subscript n with a capital P and a lowercase r. The P stands for the word permutations. Now the other values in the problem, n stands for the number of kind of athletes we're starting with. In our problem, that would be like 5. And the R stands for the number of athletes out of that 5 we're arranging, which in this case would be 3. So if you look at this example, we're using a 5 with a P and a 3. To solve this problem, you take n factorial, the bigger of the 2 numbers, that's 5 factorial, or 5 times 4 times 3 times 2 times 1, and divide it by the difference of 5 minus 3 factorial, which would be 2 factorial. Now I could write it as 2 factorial. We know that 2 factorial is 2 times 1, which is just 2. So when you multiply the top numbers, you get 120. The bottom numbers, you get 2. You divide it, you get 60, which is what we came up with here. On your worksheet, see if you can solve the next few problems. That would be problems 5, 6, and 7, and we'll take a look at those in just a moment. For number 5, consider the word math. We're going to make a list in 5A of all the 2-letter permutations that can be formed from the word math. I've listed 2, MA and MT. You could finish this off by doing MH. And then starting with each other letter here, starting with the letter A, you can make 3 words out of the A. You can make am, at, and ah. Using the letter T, you could do TM, ta, and th. And using the letter H, you could go HM, ha, and hit. And if you count up all these different possibilities, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possibilities altogether. Now, using option 1, the multiplication of descending numbers, to find out how many permutations can be formed consisting of 2 letters, remember we have a 2-letter word of which there are 4 choices for the first letter, any letter M, A, or T, or H. If we choose one of these letters, that leaves us with 3 possibilities for the second letter. And if you do 4 times 3, there's that number 12 that we noticed in the first example. Using option 2, what we can set up is something like this. We have 4 letters, and we're going to arrange or do a permutation with 2 of them. What we do is we take the bigger of the numbers in the numerator and we take its factorial. In the denominator, we take the difference of these 2 numbers and we take its factorial. So this is 4 factorial over 2 factorial. And what's kind of cool is if you list the numbers 4, 3, 2, and 1 up on the top and 2 and 1 on the bottom, like any good fraction, common factors will cancel. So you could actually cancel out the 2's and 1's, and there's your 4 times 3 again. For number 6, there are 12 players on a basketball team. Positions on a basketball team are point guard, shooting guard, small forward, power forward, and center. Using option 1, how many different lineups consisting of a different player at each position are possible? Well, one thing you could do is list the 5 positions. You have 12 options for the point guard, and if you choose one, that leaves you with 11 players left to play shooting guard. If you choose one of them, you have 10 players left to play small forward. If you pick one of them, there are 9 players left for power forward. And if you pick one of them, there are 8 players left you could choose from to play center. Multiplying these numbers together gives you 95,040, and that's the number of different lineups, which is quite a bit. Using option 2, you could set up something like this: 12 players, and we want to arrange or do a permutation with 5 of them. In your numerator, it's 12 factorial, and your denominator is the difference, 12 minus 5 factorial. So this is 12 factorial over 7 factorial. When you do 12 factorial, it's 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And when you do 7 factorial, you'll notice a lot of the same numbers: 7, 6, 5, 4, 3, 2, 1. If you look at what cancels, which would be your 7s, 6s, 5s, 4s, 3s, 2s, and 1s, you're left with the same 5 numbers that we multiplied in part A. So it should be no surprise your answer is still 95,040. The last problem we're going to look at today is a teacher wants to take a class picture. The class has 15 girls, 10 boys. Students will be lined up from left to right in a single row. How many ways can the students be arranged from left to right? Well, it just says students. Gender doesn't matter. There's 25 kids altogether if you add 15 and 10 together. So we basically have to arrange 25 people. Obviously, a person can't stand next to themselves. So what we're going to have is what we've had in the past here. We're going to start counting out from 25, and it's going to look like 25 factorial. 25 times 24 times 23 all the way down to 1. Now, there is a factorial button on your calculator that you can use. If you want to type it out the long way, you can type out all the numbers 25 times 24 times 23 times 22 all the way down to 1. And when you do this, your calculator is going to give you a number that might look something like this. It may say on your calculator something like 1.55 E25. Now, this is computer language or calculator language, and it's really saying, this is scientific notation, it's 1.55 times 10 to the 25th power. This is equivalent to taking this decimal place and moving it 25 places to the right. if you do this, you end up with a number that's like 15 septillion, which is incredibly huge, which tells you there is a whole lot of ways of arranging 25 people in a class. Now in 7b, if I say all the girls have to be on the left and all the boys have to be on the right side, there are 15 girls, so all the girls are on the left, all the boys are on the right. There's 15 girls, they can be arranged 15 factorial ways. The boys can be arranged 10 factorial ways. We multiply all these numbers together. It's sort of like 15 times 14 all the way down to 1, times 10 times 9 times 8 all the way down to 1. When you crunch this out, you get a number that's a little bit smaller. Again, you're going to get some scientific notation language. It's going to look something like this: 4.745 E18, which is equivalent to 4.745 times 10 to the 18th power, which is like moving the decimal place over 18 times. This is equivalent to 4 quintillion, 745 quadrillion, so on and so forth. Now let's see if you can solve problem 7c. So for part C, how many ways can the students be arranged if all the girls are on one side of the room and the boys are on the other side? On part B, we talked about what it would look like if the girls were on the left and the boys were on the right. That was equal to 15 factorial times 10 factorial. Now, if we have the boys on the left side of the room and the girls on the right side of the room, it would be 10 factorial times 15 factorial. Well, both of these cases you're getting the same number, this 4.745 times 10 to the negative, or times 10 to the 18th power. And what we're going to do with these two values is we're going to add them together, because either the boys can be on the left or they can be on the right. And when we have these OR problems, it typically means we add. So we're going to add these two values together. And the sum of these values actually ends up being about 9.49 times 10 to the 18th power. That is a lot of ways of arranging kids, isn't it?